Hello, welcome to ESC Live. We are live here at Langage Anaerobic Digestion Plant to learn all about how your food waste gets turned into energy. So we've got a wonderful team of experts here today, and remember you can ask questions live throughout, so make sure you make the most of that. I'm Dr Alice Mills. I'm one of the founders and directors of Exeter Science Centre alongside my colleague here, Dr Natalie Whitehead. And presenting with us today we've also got Professor Adam Feldman, who is a professor at the University of Exeter in renewable energy. And we've got this other wonderful team of experts here, so you'll get a chance to meet all of them throughout the event today. So remember to fill in your worksheets as we go along and ask questions. So hi to Year 7 and 8 at Ivybridge Community College. Thanks so much for joining us. So Adam.
Yes. Hi everyone. We're here today to have a lesson all about energy. The energy that runs everything around us. The stuff that possibly your parents grumble about because they have to pay for their energy, their electricity and their gas. So what is energy? Energy is all about how things work, how they run. Energy is the stuff that makes your computer work, your telephone work, the light make light, the cooker cook food, the microwave oven work, aeroplanes fly, cars run. And most of that energy we still get in the United Kingdom from fossil fuels, things like oil, gas, coal. But it can't go on like that because these fossil fuels are polluting the atmosphere, causing global warming. And what I teach at the University of Exeter is all about renewable energy. So what is renewable energy? It's the types of energy that are replenished as fast as we use them up. The fossil fuels take millions of years to reform, but renewable energy comes time and time again from minute to minute. And there are 7 varieties. There's sunshine energy. It's a gloriously sunny day. And of course, you know about photovoltaic panels and heating water by sunshine energy. There's wind energy from our wind turbines, wave energy, hydro energy, water coming down a river and through a turbine. And there's biomass energy. Today is a bit about biomass energy. It's the energy that gets into things like plants and animals, living material. And there's 2 other kinds of renewable energy: tidal energy due to the movement of the tides, and geothermal energy, heat from the ground. Now, with biomass energy that we get, we use it ourselves in the food we eat. We have a problem. When we get leftover biomass, pieces of leftover food, we have tended to throw all of that food into landfill sites or waste. And as that food decomposes in the ground, it firstly is a waste of that energy, but it gives off carbon dioxide and methane gases into the atmosphere. And that contributes to our global warming. And what we've come here today is to find out a better way of dealing with that waste food material. It's called anaerobic digestion, and we're here today at Langage Farm Anaerobic Digestion Plant, and we're standing on top of large tanks that digest that waste food. And to help us understand, first of all, I'd like to introduce a colleague, Dr Kev Hughes. Kev and I worked together at the University of Exeter. In fact, we studied renewable energy together. And Dr Kev is an expert in anaerobic digestion. He actually became a doctor, a PhD, a doctor qualification from studying this process that's beneath our feet here. So, Kev, can I ask you, first of all, why are we here today at this plant?
One of the main reasons why we're here today is we have waste, as Adam said, from all different forms and from all different sources, some of which we can deal with. By just taking them out and recycling them, making them into other things that are useful. But what's left is we have waste that can be dissolved by different sort of bacteria and different things in the atmosphere. It happens in different ways. If you think of the waste that comes out of your house, we have garden waste maybe that could be turned into compost by a certain type of bugs and bacteria. We have the plastics and the metals that can be moved to the side because they can't really be dissolved. But we also have all the other stuff, the smelly stuff. Imagine your kitchen bin, and that stuff there can be eaten and consumed by anaerobic bacteria. And these ones that don't need oxygen, they just sort of chew up the waste and they produce gases by chewing up that waste.
So what is this anaerobic digestion process that you're starting to tell us about here?
Well, anaerobic digestion is just the breakdowns of things like fats and acids. And that can come from lots of things, from food waste through to grass, cow slurry, all these sorts of things that are waste products can go into a process, and then we have these bacteria that sort of consume it, and by doing so they make products. And they might have some who consume certain acids and make carbon dioxide. You have some that make other acids, others who make methane gas. And what we can do is capture that in a system, try and control it so that we get out at the end what we want. And in this case, it's methane gas.
Now, it's really good, isn't it, capturing this methane gas? Because if methane gas gets into the atmosphere, am I right in thinking that it's 28 times more globally warming to the planet than just carbon dioxide is?
It is, yes. It's far more damaging than carbon dioxide in the atmosphere. Although it stays in the atmosphere for a shorter period, it is far more damaging. So if we decide not to anaerobically digest it in a controlled, closed environment, then it just escapes into the atmosphere. And we have we witness the climate change that we're seeing now. So if we can contain it and take that product, that damaging product, and use it, then it's to our benefit because we can make energy out of it and it doesn't escape to the atmosphere.
So if we just put it in the ground in a landfill site, am I right in thinking the methane would escape? And here this plant is basically to overcome that problem.
Exactly. In the ground, it would gradually seep out and escape, and it also stays down there for about 200 years, which is a long time to manage it and control it. Where here, it's in this system that we're standing on today for about 60 days. So the stuff that comes in new, 60 days later, we've got the product, the methane we want, and what's left, the digestate, will then be used elsewhere.
Just before we pass over to our tour, can I ask, are these plants here, like on Langage Farm, are they common, or would we see these regularly in the country already, or are they quite rare?
10 years ago, they were quite rare. But Langage is one of the pioneering companies to go down and control it and produce them at scale. So now they're becoming far, far more common. Although we still have problems with smaller systems, the bigger systems like this you see are occurring now and are rolling out across the UK.
Thanks very much, Kev. That's superb. I think we are heading off on a tour, and I'm going to pass over to Alice, or Natalie, and Gary.
I'm Dr Natalie Whitehead. I'm a former engineer turned physicist and one of the co-founders of Exeter Science Centre, and I'm delighted to be here today to speak to one of the creators of this amazing power plant, Gary Jones, who's kind of the technical director here, and alongside Ewan McClelland as well, who is involved in the compliance and making sure that everything runs smoothly. Maybe if we just start, perhaps Gary, if you can tell us a little bit about the motivation. Why did you make this amazing power plant?
Well, some years ago, we still are a dairy, and we actually produce clotted cream and ice cream, which are our main products. But we were generating waste. Whenever you make a product, you generate a waste, and we needed to find a better option of just throwing this waste away. And not only did we produce solid waste, but we produced a lot of liquid waste. And when we put that liquid waste onto the ground, it actually had the opposite effect to what we hoped, where it actually slowed the growth of grass, because we actually started drowning worms and things like that. And without the worms in the soil, therefore you don't get the decent root structures, and therefore you don't get the grass. The cows don't eat it, the milk becomes less, and so it's a financial spiral into going downwards, unfortunately. So we had a look at different technologies out there, and we looked at things like reed beds to try and clean up the water to put it in, but because of the way the milk works, it didn't really, milk fats get into the gate cells of the plant, so that didn't work. So we came across anaerobic digestion, and as I earlier mentioned, we were quite a fledgling sort of field in its time, but taking all things in consideration, where we were as a business, where we wanted to go as a business, how we wanted to maintain the health, not just of our soil, but by having good soil, we had healthy cows, and therefore would deliver better milk products and cheaper milk products. We moved in, and we took a risk on going into anaerobic digestion. There are lots far bigger now, like with a lot of things, economies of scale go up. So we were bigger when we were built, but now the plants are 4, 5, 6 times our size. That doesn't always work very well, because what we put into this plant is food waste, and unfortunately England as yet doesn't collect food waste everywhere, so it's still a struggle.
So this is something that hopefully, in future we'll have more food waste collections and things, and this is something we'd like you to think about all the way along. Food waste is a really important thing to deal with and process, and that's why it's wonderful that they're doing it here. But of course, we need to waste as little as possible in the first place. I wonder, so I can get these wafts of I really wish you had smell-o-vision, because it really is ripe, the smell that we're going to experience very shortly in the actual plant itself. But maybe you can tell us a little bit about the process.
Everything that's in the food is actually come from the sun for the energy, and then it's all little minerals and elements. They all get put together with the sun, and then when they come into us, our bugs break it all the way back down, and they put it straight back down to what it was when it first started growing as a blade of grass or an animal. The bacteria just biologically decompose it. Okay. So we're actually a biological solar farm, really.
Right, and so it produces methane, and that methane you take, and what goes...
The nice thing about methane is it burns, and it burns very well, because we've got the hydrogen, and when we rip the hydrogen off, we get all this heat off. So when we've got this energy, which again is actually the sun energy, we're actually releasing this methane in an engine, which is a combustion engine, and at the end of the combustion engine there's a generator which rotates quite quickly, and the mode of rotating in magnetic fields produces electricity.
We get some electricity out. Okay, so think about the energy transfers that are going on in this process. That's one of the questions on your worksheets. What's the energy transfer here? So we've got some kind of chemical energy that we start with, produces some heat that turns into kinetic energy, and then we get some electricity and some excess heat energy as well. Let's go on that tour and let's have a little look round the site. I have to tell you, the smell is rather strong. Oh, right, so let's have a little look over here. Oh, right, so we've had a food waste delivery in, is that right? So maybe we can send the camera down there to get a look at that.
So there's 2 wastes in at the moment, and for you that are local, you can see in the pit, it's full of crisps, and actually comes from Bert's crisp factory. So there's quite a lot of energy in that. There's the fat around the crisp and the potato itself. So carbon nitrogen, good ratio. And this one is actually picked up from schools in Plymouth today.
Ah, right, so maybe some of this came from Ivybridge. Wowie, it's loud.
This is the joy of food waste. And as you can see, it's food, it looks horrible, however, it's a nice mix really of carbon and nitrogen. So we get the carbon from the vegetables, and we get nitrogen or high proteins in the meat. So it actually looks quite good. It's not nice to mix with your hands, so we use a crane to pick it up and start it moving around the system. And I think everybody's feeling quite sick with the smell, so we'll move down.
Yeah, but let's move on then.
So one of the things, because it is food waste, it's all dirty, and cleanliness is everything, which is why we have an environmental manager, Ewan, who you may speak to later. So when the lorries have been in and tipped, they then have to power wash themselves and clean to make sure they don't carry any diseases up the road.
Where does it get broken down into?
So at this point it goes into the machine we saw earlier on, and it gets split into 2 fractions. One you can see behind me is the packaging. So that's all the bags and the containers that were in there, and the machine we were looking at upstairs it splits it into two. So the plastics go into one, and then we send that off to MVD, which is an incinerator. And then the organic fraction actually travels down that chute there, and then we compress it, we heat it, and the reason we heat it is we need to cook it, and we like to cook it so all of the bugs that are in there, they aren't necessarily the ones that we want. So we pasteurize, as it comes, we pasteurize them just like you milk at home, we kill everything, and then we add the bacteria that we want, which is essentially from a cow's stomach.
So it's all about getting the bacteria to be happy. First of all, getting rid of the bad bacteria. Getting the bacteria is going to produce loads of methane, and then using that methane to then burn it and generate electricity. Fantastic. I think we're going to go outside where it's a little bit quieter, and we'll be able to also get some nice fresh air. What are these tanks that we're standing on?
So these are effectively cow stomachs.
Oh,
And that's what we... But nature is far better at doing this than we are.
right.
So a cow will eat grass, and 6 hours later you've got methane and slurry. With us, depending on what food it can either take something like 15 seconds or 2-3 months to fully break it down back into the methane that we're looking for. So because it is a mixture of everything, we have to keep it all in there for the longest period of time. But essentially, these are 3 cow stomachs, just made of concrete. And just like a cow, it walks around to move the stuff. The bugs that are in the tank can't swim. So we have to stir it continuously to get them to bump into each other and interact, and then to get the end result that we want.
And you collect that methane, and then where does it go?
So all the methane comes off, and if we travel this way, they all end up in a big plastic bag. Looks a bit like a bouncy castle.
Okay. Wowie. Whoa. Yeah, it just also smells. It's a very sensory experience.
You can smell a bit of hydrogen sulfide.
Right.
So unfortunately, you don't just get CO2 and methane. There's all other things you get in there. One of them being H2S, which is hydrogen sulfide, and that's actually the rotten smell in the fart.
Ah, right. Nice. So I think we're coming towards the end of the tour now, and we're going to be passing over to Alice. But any more questions have they come through? I think you were going to point out something quite exciting
So let's see
as well,
the power of the methane.
Right.
If you can just look up.
Oh, yes. There.
So that is the power of the methane once we ignite it. So you can see the energy that's released, and that is sunlight energy.
Okay, so thank you so much, Gary, for that. That was brilliant. And we're going to have a chat with you a little bit later as well. But we need to pass on to you guys so you can do your challenge.
Brilliant. So you're going to have a quick challenge now, and this is called a Fermi challenge. Fermi was a scientist who was incredible at estimating things without very much information. And this is a really useful skill for all engineers. So yes, you can calculate something properly, but how do you sanity check your answer? How do you check it makes sense? So you're going to work out the answer to the question. Estimate how much energy could be generated from the food waste produced by your school in 1 year. And the only bit of information I'm going to give you there is that digesting 1 tonne of food waste can generate about 300 kilowatt hours of energy. So have a good think about that. You've got 5 minutes. Good luck.
Thank you for working away at your challenge answer. So what we've asked is, how much energy do you think that your whole school in one school year can produce from its food waste? And we're getting some answers through now. But let me run through how I'd go about calculating this, and you can see if it's the same ideas that you've been thinking about. Well, first of all, we want to know how many people are there in Ivybridge School. There's 2,400 pupils, I believe, and about 350 staff. 2,750 people. How much food waste did you think each of the people there produce each school day? Well, actually, when I stopped to think about it, I myself thought, well, it's about 100 grams a day if you count all the banana skins and all the apple cores, bits of leftover sandwich and so on. But we went to a study that examined what every school was looked at across England, and we found out that every primary school, you're a secondary school, children produce about 75 grams of food waste per day. But in a secondary school, it's 40 grams on average. So we multiply the 2,750 people times 40 grams by the number of school days in a school year, which is 39 weeks or 195 days a year. And we find out that your school is probably producing about 22.5 tonnes of food waste per year. And if 300 kilowatt hours, a kilowatt hour is the unit of energy that we buy our energy in, if we multiply the 22.5 tonnes by 300 kilowatt hours, we find out that your school produces around 7,000 kilowatt hours of energy that we could get from a plant like this a year. That is enough. I did some calculating to run my wife's Tesla car for about 26,000 miles or 2 years use. Or how long could we keep an LED light bulb on from the food waste that your school produces a year? Well, it's about 77 years continuously. So there's your answer.
Great, and we had some really good estimates from various different classes there. So we had about 18,000 kilowatt hours and we had about 15,000 kilowatt hours. So those are slight overestimates, but still, not bad for estimating with very little information. So
in the right order. That's fantastic calculation.
And you might be a particularly wasteful school. Who knows? That might be right. Okay, brilliant. So handing over to you.
Fantastic. So you've done your engineering challenge now, everyone, and I'm going to very, very quickly just speak to Kev for a little bit about the future of anaerobic digestion. Hopefully you've seen how cool this place is. Really does smell, but it's very, very cool and really important to use up the food waste. Kev, can you tell us a little bit about where you see this going? Do you think we'll have these everywhere? Will we be processing food waste in this way everywhere in the UK?
Yes, we will. The future of anaerobic digestion obviously relies on the future of the waste streams, and there's so much out there that we don't actually take advantage of at the moment, ranging from there's cow slurry, there's food waste, there's grass, where I've been doing a lot of work recently, but also things like your sewage, all your poos and everything, all that sort of stuff can go into anaerobic digestion because they love eating that sort of stuff. So what you find is some of that is being utilised really well, like the sewage. But a lot of it is being missed. So the challenges of the future really is, one is it will be a massive industry if we actually manage to collect properly and collect everything that we can collect and fully utilise it, rather than it going into landfill or waste elsewhere. Because you can imagine the stuff you've seen here is quite wet. So if you burn that, it takes a lot of heat to burn it off before you can get the energy, so it's a little bit wasted. So what we can do is we can take waste in the future, look at plants like this alongside maybe composting plants, which eat food that these bugs don't really like. You've then got the anaerobic digesters, and then we've got like incinerators, which you've seen before, taking the stuff that the bugs just can't eat and burning it to give us energy in that form.
So we need to think about waste in a totally different way. At the moment, it's just something that, or at least previously, put it in landfill, get rid of it, or, but now we can think of it as a source of energy that we need to think a bit more, holistically about how can we reuse all of the waste products and make something really good.
Exactly, yeah. Waste equals fuel. Whichever way you deal with it, it equals fuel. Obviously, we try and avoid it first, but if we can't avoid generating the waste or we can't use it for other things, then let's turn it into fuel and use it as fuel. But we need to do it across the country and at all different sizes. We've seen a big plant here where there's lots of places where they could do it in small scale, little microsystems, and that's probably one of the main challenges now is tackling the microsystems. So you'll see these a lot more across the country. We have very few of them in this country. For example, in India, they've got about 4.6 million of them. Wow. They're done all over the place, in people's gardens, in market stalls, everywhere.
So we need to catch up in this country,
we do,
I think.
Yes.
Ewan, we've got these kind of wood chip piles here and this big kind of green tank.
Okay, that's our biofilter. And what happens is the two pipes suck air out, so we've got negative pressure on the building, and that sucks out all the odour, obviously not all of it, because you smelt it. And the air goes underneath the biofilter, comes up through it, and the bacteria eat away at the odours. So that's one of the compliance things I've got to deal with. This one here is the engine.
Right.
So the gas goes down this pipe, round the back, and goes into the engine.
Right.
That generates electricity, which you talked about before. But the extra thing with this is the exhaust. Instead of releasing it to the atmosphere, it goes into a boiler. Right. And that heats up water, which we use for pasteurisation system. So nothing's really lost.
Brilliant. So you've got electricity and some heat out of there. Fantastic. Yeah. Combined heat and power, really important in engineering. Thank you so much, Ewan. Let's pass over to Alice to get your careers questions answered.
One of the questions was heating to kill microbes, ? Because I suppose that question might be about if you need microbes to digest the material, why do you heat it?
What we're trying to get rid of are the pathogens. So those what we actually got in the tank is like Yakult, if you want. It's a very healthy bacteria. What we don't want are pathogens, which are things like Salmonella and E. coli. So those are the ones we're eliminating. So the bugs that we want in there are nice and healthy and don't really have to compete with anything.
Brilliant. Another question was, does it take non-renewable energy to run the machines?
No, we call it a parasitic load. And that means that out of the 500 kilowatts that I'm producing, I take about 35 kilowatts continually to run the plant. So when you first start it up, the very first time you turn the bugs on and you turn the engine on, you've used a load in from outside, but once you're up and running, there is nothing in from outside.
Brilliant, that's so cool. What else have we got here? Sorry, I'll just scan through. Arthur wants to know what gets produced when you burn methane. And actually, you've just seen the engine over there. So
okay.
yeah.
It's actually CO2. Now, that sounds really bad. But as was mentioned earlier on, methane is 28 times worse than CO2. And what we do is we convert that from 28 times worse down to 1 instantly. But again, the only carbon that gets absorbed or gets released is the amount of carbon the plant absorbed from the atmosphere whilst it was growing. So it is absolutely carbon neutral. We can't make carbon, we just recycle it.
Brilliant. Fantastic. We've got a question here, which I guess actually is to you again, Gary. So Edred wants to know how much is the upfront cost? So I guess to build all this, and it was a while ago, wasn't it? So.
It was a while ago, and of course upfront costs change. This plant cost somewhere in the region of 4.5 to 5 million, but the returns are great. And these places tend to be built for financial gains. So providing the return is greater than the upfront cost, people will do it. However, at Langage, we didn't just build it for the return. As long as it was neutral, we felt it was the right thing to do.
Maybe we could just have a little very quick summary from each of you of how you ended up in this, because none of you started out necessarily dreaming as a 5-year-old of getting into AD. So yeah, I don't know, did you? So yeah, maybe if we go around quickly and each of you says sort of your path into this.
Well, I joined the Navy, I left Wales and joined the Navy at 16 some years ago. I did my career, and whilst in the Navy I became an engineer, and I managed to use all of those skills I learned there in AD, because essentially we produce power, and when you're on a warship, that's what you are. You're just producing power so you can utilize it. So the crossover skills for me were quite simple. I did have to learn about the biological side of things, but that's just get your head in a book and read.
Fantastic, thank you. How about you, Adam?
Hi, yes. Ever since I was a schoolboy, I've absolutely loved science and machinery and why things work. I used to always build with my Lego and Meccano and other toys. But when I finished school, I went off to train as a medical doctor, and I ended up an orthopedic surgeon, which is a kind of human engineer for 20 years. I used to put people's bones and muscles and broken bits back together again. But then one day, as I was going between my hospitals, I watched big wind turbines being put up, and I thought, that's a fantastic type of machine they're building. So I went off to train, do a second university degree in engineering, and it was just such a brilliant subject that I wanted to stay on at the university and teach people all about these fantastic machines. And I adore being at plants like this today. So there you go.
Hi, it's Kev again. Right, I took a different path again. When I left school at 17, I decided to join the Royal Air Force. So I went there for 30 years, flying around in aircraft and enjoying myself, and then decided that I wanted to change. And I saw renewable energy engineering, which was starting to become quite interesting and coming to the forefront of the news. So I went to New Zealand for a year and checked out the scene there, decided I wanted to be a renewable energy engineer, and returned to the UK. And I actually went to university at the age of 50. This is where I met Adam, who was on the same course as me. And there learned to be an engineer, and as I came towards the end of it, they asked me if I'd remain and do a doctorate in a certain aspect of anaerobic digestion, which was taking, we heard how you have to mix, and what I was looking at is how to calculate the amount of mixing required to get the job done. And then I went off and did some research in that field.
Yeah, so I joined the Army, 18 for 22 years. Came out of that, did construction for a couple of years, and then became a tattoo artist. Did that for about 15 years and got into environmental health. Did a degree on that and came here as an operator. I think I was operator for about a year, and then Gary offered me the opportunity to become compliance manager, and that's what I've been doing for the last couple of months now.
Brilliant. So we've got a couple more questions I'd love to ask. So one is how many engineers work here at Langage?
We've got 5 engineers,
Brilliant.
All with varying degrees of skill. So some fully apprentice, and some just learning, and some we put through apprenticeship schemes.
Brilliant. And another one is aerobic digestion more efficient than other renewable energies? I think they probably mean anaerobic, sorry, yeah.
I hope so. It is efficient because it's one of the, you actually get a lot back. Incineration is good, but you have to burn the right things. There's no point burning a carrot. You have to put more energy in than you get out because effectively you're boiling water. But if you're burning waste plastics and things like that, then it's a fantastic second use for those materials.
Brilliant. And another one about, do you offer any apprenticeships here at Langage?
So yes, we do, but as there's only 4 people, it's not big enough to run continuous apprenticeship schemes.
Yeah, fantastic. Thank you so much for listening. We hope you've got a lot out of this and really enjoyed meeting these people from really interesting backgrounds, all doing something fantastic for the world, generating energy from stuff that we just chuck away. It's brilliant. So, Adam.
And a 20-second recap of what we've learned today. We've learned what anaerobic digestion is. It's a fantastic way to prevent the methane gas from food waste going into the atmosphere. Instead, we capture it, we use it, we turn it into useful energy. You've worked out a challenge, how much food waste your school works that can be turned into energy. And most of all, you've learned what fun it is to be an engineer. It's a great career, and I encourage you all into engineering to develop, build and run amazing plants like this.
Thank you to our amazing engineers, Gary, Kev and Ewan, thank you so much. And next challenge for you guys is to fill in the feedback forms. Please tell us what you think about this event. Give us your feedback and let us know. That's for the teachers as well as the students. And that's it. Thank you very much from all of us here. Bye.